All right, let's get going. Starting out a new course, geometry. Quick stuff about me in case you don't know me. My name's Donald Timpson. Education background. I switched my major a lot when I was in college. Switched from healthcare to finance to engineering to computer science, but ended up double majoring in math and computer science. So math, one of the things I know pretty well. Professionally, I work as a software developer, software engineer, create iOS apps for the iPhone. That's what I do professionally, but obviously spend some time as a volunteer teacher here. Okay, so starting out this class, geometry, one more piece of housekeeping, I guess. I record all my lectures and I upload them to my YouTube channel. So just search my name, Donald Timpson, on YouTube. You'll see me. There's a picture of me. Hopefully you can identify it. And then, under playlist, I'll have a playlist called Geometry 2024, and all the videos will go into that playlist. If for any reason you have any trouble accessing materials, you're always welcome to email or text me. I prefer you text me, but email's okay. Email just means I'll get back to you in like 4 days or whatever. Text will be immediate. So you can always reach out as needed. So that's housekeeping stuff. Any other housekeeping stuff? Last thing I'll do once we get our schedule completely figured out is I will email you all a copy of the book and the syllabus. Because Masada's probably out of books by now. You probably all went and got the hard copies that there were. So I'll also send those to you. You need to make sure in Gradebook that your email is up to date in Gradebook, because that's the email I have for you. Make sense? Mm-hmm. Any other bookkeeping and any other questions before we jump to the material? All right, so let's get started with the actual material now, geometry. Looking at etymology, what does geometry mean? It literally just means earth measurement. It's the way that ancients started measuring the earth. They started using geometry. So, a little bit of history about geometry. Mathematics in general, geometry was the first field of mathematics to develop. So when you look at the development of mathematics early on, you have the Babylonians and the Egyptians, for the most part, are the ones making mathematical observations. But at the time, it's just a bunch of empirical data. You understand what empirical data is? It's just brute fact observations. You're not creating any theories or anything like that. You're just seeing what's before you. I tried to measure the sum of this triangle's angles the best I could, and it looks like it came out to 179.2 degrees. Just empirical data. So they started collecting a bunch of empirical data. Mathematics proper doesn't start until we get to the Greeks. It starts with this man by the name of Thales. So Thales, going back 625, 540, here's his date, so we're looking at roughly 600 BC, we finally get geometry starting. And what does Thales do that makes math start? He starts this concept of proving something. Being able to actually prove something. If you go back to the ancient Babylonians or the Egyptians, they knew that if you took a triangle and you made this edge 4 cubits, and you took a triangle and you made this edge 3 cubits, then this angle was really close to 90 degree, or sorry, making a triangle that way, with 3 and 4. You know from the Pythagorean theorem, 3, 4, 5. They knew that this angle was close to 90 degrees. They knew it was close to a right angle, and how often do you need in construction a square to make sure something's a right angle? The Greeks saw it's exactly a right angle. The Babylonians, the Egyptians, they say, who cares? It's good enough for our purposes. They had an approximation for pi. They said it was 22/7. The Greek says it's exact. They said, who cares? It's close enough for what we're talking about. And they had their approximations for the square root of 2 and all sorts of stuff. They had their arguments for where they knew that the angle sum of a triangle was close to 180 degrees. The Greeks said, is it exact? Is that the case for all triangles? The Babylonians did. And the Egyptians, it's largely, who cares? It's good enough for our purposes. So it's the Greeks who introduced this notion of actually, they're the ones who are now interested in knowledge for the sake of knowledge. This is the first time this has really happened. We want to know if that's a perfect square for this perfect 90 degree angle for the sake of knowing whether or not it's a perfect 90 degree angle. We're not just looking at applications. And the second thing they're going to do is introduce this concept of a proof. Is there a way that we can prove that this will always be the case? The Babylonians notice it's a cute fact. It keeps happening. Will it always happen? Who cares? It works for the ones we're using. The Greeks want to know, will it always happen? And we'll do that in this class. We will prove that no matter what triangle you choose, its angle sum will always be exactly 180 degrees. Think about how crazy that is. It's going to be a nice simple proof, and we're going to prove a fact about infinitely many objects in a few lines. The idea that this was even possible was a breakthrough in thought. So that's what the Greeks did. That's what they did with this introduction of geometry. So it starts with Thales, this concept of proving something. We move on to Pythagoras and the Pythagoreans. They're pretty famous for probably the most famous theorem in geometry. What is it? Pythagorean theorem. And we go to Plato's Academy, where tons of geometry is trying to be developed systematically. So, first off, Plato's Academy, first institution of higher level learning in the world, or at least one of them. It's where our school gets its name, the Academy. It comes from Plato's Academy. Plato's Academy is the first academy. What is academia? It's what they did at the academy. Who are academics? They're people who attend the academy. That's where all this gets its roots. So it goes back to Plato's Academy. Now, he famously had inscribed above the entrance, if you want to go to his institution of higher level learning, "Let none ignorant of geometry enter here." Why on earth did he have that above the entrance of his academy? Was he saying, if you don't know if you haven't memorized a bunch of geometric conclusions, we don't want you? No. He cared that you knew how to think. Here's another reason that we love geometry so much. It's such a safe ground for teaching you. Because in geometry, when you make a mistake, you demonstrably made a mistake. I can demonstrate to you exactly what your mistake was. And so geometry is a wonderful pruning ground for making sure that you're thinking correctly. So he wanted to make sure that you knew how to think before you were allowed to enter his academy. Fortunately, modern education focuses way more on having you form an opinion rather than teaching you how to have a well-formed opinion. And so you're told over and over again, what's your opinion on this? What's your opinion on that? What's your opinion on this? Before you even know what deductive, inductive, or abductive reasoning are. So he didn't want you forming opinions on politics and ethics until you at the very least knew how to think critically. You knew how to reason, geometry, safe ground to that. If you've mastered this, at the very least, you can think. What did Plato and these early academics think was the ideal curriculum for you to go through? They thought first you should go through arithmetic, pretty much what we think of as algebra, and then geometry. Plato split it into two, geometry and then solid geometry. Geometry being two-dimensional geometry, solid geometry being three-dimensional geometry. And then he says that you should go on to astronomy and music. Why astronomy and music? So astronomy at the time, they were interested in studying motion that you could see. Motion that you could see. Now, for them, the heavens is the most consistent source of motion that there is. You watch how the stars and the planets move. The way that we see it now is the same way that they saw it 2,000 years ago. And so it's a good source of motion that people can talk about over many generations. So you studied astronomy, but the point of studying astronomy was to study motion. A better word for it now would be, they're talking about studying physics. There's a reason that all your early physicists were astronomers. It's because that's the motion that they were initially talking about. And then he said you should study music. Again, he is not saying go learn how to play an instrument. He's saying you should study motion now that we observe with our ears. This is motion that we observe with our eyes. This is motion that we observe with our ears. So he's talking about pretty much what we would now call wave mechanics. And then finally, the dialectic. Here's his philosophy. That's where you get into more philosophical topics. Here's now where you start talking about ethics, politics, those types of things. Here's the type of foundation he thought you should have before you move on to higher level things. Converting it to modern language, he's saying you should go study algebra, geometry, physics 1, physics 3. Why do you skip physics 2? Well, they didn't know anything about electricity and magnetism. That's physics 2. So that gives you a sense for what these early academics thought academia should consist of. And a little bit why. Aristotle comes along. Aristotle, he's famously the father of logic and of science as we use the term now. This notion of developing systematic bodies of knowledge scientifically starts with Aristotle and his organon. In particular, his prior analytics and his posterior analytics is where he sets up those foundations. As Plato set up his school at the Academy, Aristotle set up a competing school called the Lyceum. And so Plato's initial model that he set up starts being reproduced at other institutions. Good so far? Just a bit of history. And so what we've got now laid down logic, and he showed how logic is foundational to every field of study, in particular geometry. And so, it became obvious that we should start studying logic before we study geometry, because you use logic in your development of geometry. And you use geometry, for example, in your development of physics. So you can use logic to develop your geometry. You can use geometry to develop your physics. You cannot use physics to develop your logic. You cannot use physics to develop your geometry. And so Aristotle introduced that logic is at the foundation of any field, including geometry. Now we get a man who comes along by the name of Euclid. Euclid, famous for his work, Euclid's Elements. What did Euclid do there? He took this geometric body of knowledge. He understood that we're going to presuppose Aristotle's organon. We've got to make my square for geometry bigger. And he showed how you could take all these geometric proofs that are known, and you could organize them into this logical structure, so that from 5 initial postulates, 5 assumptions, you could derive every single one of those proofs, those truths. So we have all these geometric theorems that are known in math. One of these is the Pythagorean theorem. What Euclid did was he said, look, these two together entail that theorem. This together with this entails that theorem. These two together prove that. And he created this logical structure proving everything from 5 initial postulates. So Euclid showed how if we take Aristotle's logic and we start out with these 5 postulates, we can derive all the known geometry of the day. And this becomes a standard by which we set up systematic bodies of knowledge. From here on out, everyone is trying to reproduce in their respective field what Euclid did in geometry. If you go all the way to physics, if we were talking about Newtonian mechanics, it's the same type of system. It starts out with its initial postulates or axioms, and it sees what's true from those initial postulates or axioms. So if we put physics up here, what are our 3 starting postulates or axioms in physics? In the natural sciences, we call them Newton's laws. Newton's laws aren't things you prove. Newton's laws are things you validate and you assume. And so, an obvious motion remains a motion unless acted upon by a net force. You've heard something similar to that, etc. For every reaction, there's an equal and opposite reaction, one that you've heard. So those are Newton's laws, and you start using those to develop your field of physics. So it's the same thing that Euclid did down here in geometry all over again. Every field of study tries to do this exact same thing. So Euclid's Elements becomes the standard that everyone's looking to when they start developing fields of knowledge. So Euclid, he combined all known geometrical theorems into 13 books. We call them the Elements. And he made so it all comes from 5 postulates. So 5 postulates from geometry, and then 5 common notions. Those are results from logic. We'll develop the notion of a theorem of logic in a second. But that's Euclid. So now, what does a curriculum look like after these guys get it all set up? So Aristotle introduced logic. Euclid, he developed geometry this way. Plato started the academy the way they did. From roughly the year 500 to roughly the year 1500, this was your core curriculum. You would start out with the, I don't know if it's tri or trivium, I'll call it. The trivium, where you would first study logic, grammar, and rhetoric. And then you would move on to your more advanced courses, which would be arithmetic, geometry, music, and astronomy. Music and astronomy there, meaning what they meant at Plato's Academy. Studying motion, sound motion, and studying motion that you can see with your eyes. So this was your core curriculum for almost 1,000 years, give or take. And it's pretty similar prior to that, from roughly 500 to 1500. Now, for some reason, for some crazy reason, logic gets removed as a standard course in education around the year 1900. How many of you have taken a full logic course before? And that's not surprising. This was a standard part of your education. It's absolutely foundational to your education, and yet you've never taken the course. It used to be everyone did, and around the year 1900, this just got ripped out of everyone's curriculums. All the schools just stopped teaching it. Why? Well, not very good reasons. That would get into some history of philosophy. And so now, what are us poor math teachers to do? We've got to teach you mathematics. All mathematics presupposes logic. In fact, logic is the only recourse of analysis we have outside of other fields of mathematics. How on earth can I teach you anything if you don't know logic? So there's a good chance that most of you probably thought logic is somehow a part of geometry, right? That's what most kids think. No, logic has nothing to do with geometry. Logic is to math what grammar is to literature. You have to use grammar in writing your literature. You have to use logic in constructing your math. The two have nothing to do with each other. This is its own field. This is its own field. Logic is not some part of geometry. Logic is logic. Geometry happens to use logic. Algebra happens to also use logic. You're not taught algebra very well. You're not taught axiomatically, but that's how it would be. And then other fields of mathematics whose names you don't know, like topology, also uses logic. So logic is completely foundational, and that's the reason that we're going to start with logic in this course. You need logic to develop your geometry. Now, well, let's see if I go on to that next. I guess we'll draw that up in a second. So first, let's talk about how you know something, and then we'll come back to talking about logic. How do you know something? Tell me one thing you know. Know with a capital K. No question in your mind. Every human being would agree with you. This is true. What do you know?
Sky's blue.
Sky's blue? Who agrees? Okay. Who knows what the sky is? Tell me when I get there. Am I there yet? Am I there yet? I'm there? Or let's start with blue. Who can tell me what blue is?
It's a color.
A color. So is green. You didn't tell me anything.
It's a wavelength of light that you can see.
What did he say?
It's a color in a different form.
It's a color in a different form. So I'm going to tell you exactly what blue is. It's a color in a different form. You now know blue. No, I told you nothing. What exactly is blue? And you're stumped. How on earth do you know the sky is blue if you don't know what the sky is and you don't know what blue is? And yet you claim the sky is blue is true, universally true. Right? That's one way we could attack that. But let's think about it. We'll take it in a more colloquial sense. Or I guess we could finish the what is blue. You can take his answer. His answer is blue is a particular frequency of light. If you get a particular frequency of light and it's in a certain range, it's what we call blue light. And that would be one way of defining it, but now he's making reference to what we call a wave, which is making reference to a mathematical object. Waves don't exist in this universe. We use waves to model things that exist in this universe. So we have to come up with some mathematical object for a photon, and we say we'll call it blue if it has this particular property. But to the extent we can be precise in our speech about things in this universe is to the extent that we have to model them with some mathematical object. You have to reduce it to a mathematical object if you're going to speak precise about it. I'm going to teach in this class perfect communication. How to speak completely unambiguously. That's what you have to do with logic. I work as a programmer. When I talk to a computer, I do so in a completely unambiguous way. If I talk to that computer, I write a program, and I give it to another computer, it interprets it identically. And I can pass that on to 1,000 different computers, and they all interpret it the exact same way. All human beings agree about some proof, all mathematicians. No mathematician says, nope, that proof doesn't really work, unless they're being pretty fancy, but for the most part, you can perfectly communicate exactly what that knowledge is. So, we're going to teach you perfect communication here. So, if you want to speak precisely about it, you have to reduce it to a mathematical object, but let's now talk about how you know the sky is blue. And we'll use it in a more high-level sense. How do you know the sky's blue? Tell me how you know. I'm looking for the reason that you think the sky's blue.
I look up.
So he looks right now and he sees it's blue. Okay, so it's blue right now. What about tomorrow? Will it still be blue? Was it blue yesterday?
It's always been blue.
It's always been blue. In your experience.
Yeah.
In your experience, during the day, every time you've looked up and observed the sky, it has appeared blue to you. Right? So that's what we call inductive reasoning. The reason that you think the sky is blue is because every time you've observed it, it has appeared blue to you. That's one way that we reason. So 3 basic types of ways that we reason. Deductive reasoning, inductive reasoning, abductive reasoning. The safest and most sure form of reasoning is deductive reasoning. Let me give you an example of deductive reasoning. I tell you that if all men are mortal, and if Socrates is a man, what do you know?
Socrates is mortal.
Socrates is mortal. You know that if all men are mortal and if Socrates is a man, then Socrates is mortal. Is that true?
Yep.
Yes.
Okay, question. Do you know all men are mortal?
Not necessarily.
Did our statement just really say, I said that bad. Did we say all men are mortal?
You said if.
We said if all men are mortal. We said if Socrates is a man, then Socrates is mortal. We never said all men are mortal. We never said Socrates is a man. We never said Socrates is mortal. We said if all men are mortal and if Socrates is a man, then Socrates is mortal. That's all we said. That's what we said is true. We said the whole implication is true. We said these two things imply this. That's what's true. This is very subtle and very important that you understand. We never said all men are mortal. We never said Socrates is a man. We never said Socrates is mortal. We said if these are true, then this is true. That whole thing is what we're calling true. And that's deductive reasoning. And that's the only type of reasoning that we use in logic and mathematics. This is the reason that all your theorems in mathematics can be phrased as if-then statements. We prove implications to be true. Over and over again, and that's what we're going to be doing. Make sense? So that's deductive reasoning. If all men are mortal, and if Socrates is a man, then Socrates is mortal. That we know for sure. What if all men aren't mortal? Who cares? We didn't say anything about that. We just said if all men are mortal, and if Socrates is a man, then Socrates is mortal. So that's deductive reasoning. Now we get to inductive reasoning. What is inductive reasoning? This is a reasoning that's the way it's always happened. And so that's the reason I think it's going to happen that way again. We already went through the example of you thinking the sky's blue. Give you another example. Find one that I can drop. What's going to happen if I stop supporting this piece of chalk?
Simple.
That's a bold prediction. All right, you figured it out. Why did you think that was going to happen?
Is it always?
Because in your experience, unsupported objects fall to the ground. Now, did it have to be the case that that object fell to the ground?
No.
No, for all you know, I rigged that little piece of chalk, I stuck a little magnet in there, I've got some electromagnet hooked up in the ceiling, and I could have turned that on the second I let go, and it could have shot up to the ceiling. Right? I could have subverted your expectations. That's what magicians do. They play on your inductive reasoning and intentionally come up with a conclusion contrary to what you expect to happen. So inductive reasoning, it's not a guarantee, it's just probable. So we take, in inductive reasoning, we observe a bunch of instances of a particular phenomenon. You watch over and over again, every time an object is unsupported, it falls to the ground. You watch that happen over and over and over again. You create this generalization then, all unsupported objects fall to the ground. Or you look at the sky, you look at the sky, you look at the sky. Every time you look, it looks blue. You create this generalization. The sky is blue. So in inductive reasoning, we take particular experiences, particular observations, and we create a generalization out of them. It's the reasoning of creating generalizations and assuming the generalization is true. You with me on there? And then finally, abductive reasoning. It's counterpart to inductive reasoning. Inductive reasoning, you create generalizations from particular experiences. Abductive reasoning, you use all your generalizations to try and reconstruct one particular experience. Common example. You're walking down the sidewalk with a friend. You feel a drop on your hand. What's going on? It's probably raining, right? But then you look up and you notice that there's no clouds in the sky. You have this generalization in your head that clouds presuppose rain, or that clouds are a necessary condition for rain. So then it can't be the rain. You look around, you notice that there's sprinklers also going on. Maybe the wind caught a drop. That's possible too, right? Another generalization you've created is that sometimes when sprinklers are on and the wind's blowing hard enough, it's able to carry a drop to my hand. And so you might think, oh, it's the sprinklers. Then you might reason really quickly, well, those are kind of far away. The odds of it carrying that far, that's not very good. On the other hand, your friend Pete isn't very good at saying Pete without doing a little bit of spittle, and you remember that he just had a particularly difficult P. And so maybe he spit on your hand, and maybe that's what happened. So abductive reasoning, you're trying to reconstruct a particular experience. So deductive and inductive reasoning, or deductive reasoning, this is the reasoning of logic, the reasoning of math. It's tautological implications. Inductive reasoning is the reasoning of creating generalizations from a bunch of particular experiences Abductive reasoning is using your generalizations to reconstruct one particular experience. Those are our basic types of reasoning. This is the only type of reasoning we're allowed to use in math and in logic. You have to start using inductive reasoning if you want to do science. If I want to know, are all men mortal, how would I find out if that's true?
You look at a bunch of men.
Yeah. So in math, we only say if all men are mortal and if Socrates is a man, then Socrates is mortal. That's all a mathematician says. A physicist comes along, he says, okay, but I want to know, actually, is Socrates mortal? So he decides he's going to go validate these two things. And so this physicist, he's got to first find out, are all men mortal? And how's he going to do that? Well, one naive way to do that is he can go follow someone around long enough, and he notices, after enough time, they fall over dead. Pick someone else, follows them long enough, after enough time, they fall over dead. He watches this happen enough times, and he says, eventually, all people die. So, generalization, all men are mortal, etc. And so that's the thinking of the physicists. Start actually describing facts of this universe. Mathematics does not describe anything in this universe. Mathematics is no way dependent upon the facts of this universe. We use math to describe this universe. Make sense? Okay, so those are our different types of reasoning. So, why learn geometry? First, basic applications. Geometry, if you go on to study more advanced things, more complex systems, geometry comes up a lot. If you go on to get what some of us call a real degree and a real job, then you're going to be doing a lot of geometry. Don't let other teachers hear this lecture. Basic applications. Number two, in this geometry class, we are now going to be focused on getting you to know things. Know with capital K. You're actually going to, in your education, know something. Wouldn't that be nice? Instead of just parroting. There's so many things that you say you know that you don't have a clue about. Do you know that the earth goes around the sun?
Yeah.
How on earth do you know that? Go outside and watch it. You can literally watch the sun move around the earth. There's a reason Copernicus was hesitant to publish his works. He was afraid everyone was going to laugh at him. Because it goes against your basic common experience. How do you know that the earth goes around the sun? Did you go out there and did you do all the charting of the stars and do all your geometric diagrams and come up with the proof? Oh my goodness, that's actually true. No, you just take it, someone told you. Someone a bit older than you, maybe wearing a tie, said something and you just ate it up. I don't want you to ever just eat up anything I say. I want you to challenge it. If it doesn't make sense, you should push back. You should be able to know everything we're talking about, not just parrot facts. Parroting facts isn't knowing anything. Amongst modern kids, you often get, not modern kids, modern culture, you get this attitude that we're so superior to people in the past. We know so much more than they did. If I stuck you 2,000 years ago, and you were with an educated Greek, what on earth could you teach them? And if you told them you know all this great knowledge, and they start questioning you, they'd find out really quick that you don't know much. They might ask you something like, what's 4? And you might hold up 4 digits, like a toddler would. And they say, no, that's a digit. What's your definition of 4? You say 2 plus 2 is 4. Okay, prove it. Demonstrate for me that 2 plus 2 is 4. And you're finding out now that a lot of your algebraic and arithmetic education, which is parroting and noticing patterns, and not actually being taught to know any of these things. So in geometry, we're going to focus on trying to get you to know. Know with a capital K. Actually know. So we're going to expose you to the difference between knowing as in parroting and knowing with a capital K as in understanding things. Second thing we're focused on is a practical skill. Improve your ability to apply logic and deductively reason. Now this is, well, these two kind of go hand in hand. Second one is to get you competent at operating in axiomatic systems. Every systematic body of knowledge that we talk about is an axiomatic system. If you go on and you were to study quantum mechanics, for example, quantum mechanics is an axiomatic system. You have your 3 axioms of quantum mechanics, and you're determining their tautological implications, and that's what the field is. If you were to go study special relativity, Einstein has his 2 postulates, and you're looking at their logical implications. If you're studying Newtonian mechanics, Newton has his 3 laws, 4th if we want to include gravity, and you're looking at their tautological implications. You're looking at what they entail. They're just axiomatic systems, axiomatic systems. That's all they are, built on top of each other. So we start with logic. The first axiomatic system we build on that is called set theory. Then we build geometry on top of that. Then you can build analytic geometry on top of that. Then you can build physics on top of that. And you're building axiomatic systems on top of axiomatic systems. Once you get competent in one of these systems, that same type of thinking rolls over to all systems. And so getting competent in geometry is helping you get competent in any other field of study you choose to go into, because it's the same type of thinking over and over again. So trying to get you competent in axiomatic systems and improve your ability to apply logic and deductively reason. And I don't know, this is the skill that pays. You want, nice and simple, I don't like to motivate you with money, but we'll do it. You want, after high school, for sure you want to go on and have a job where you're guaranteed at least 6 figures. Okay, $100,000, no question. What is the skill that is guaranteed to get you that? Do you know how to function in axiomatic systems, work with abstractions in axiomatic systems, and design new abstractions in such systems? That's the skill that pays. I don't care if it's in math, if it's in physics, if it's in computer science, if it's in engineering, whatever it is. It's the same skill. This is your first taste into that skill. So, why get paid? There's another argument. Any questions about geometry? Any questions about any of that before we start on the material proper? Go ahead.
Why did you take logic out of, like, what was the reason? I'm curious.
Oh, shoot. I may have to give you a completely unsatisfactory answer because it takes too much time. What you end up happening is you go far enough back in time, your philosophers, your mathematicians, and your scientists are all kind of the same people. They all know each other. And you get what we call specialization. Specialization doesn't mean you have a special insight to your field. It means you spend way too much time thinking about your field and not enough time thinking about other fields. And so you got math and science are developed over here. Philosophy becomes developed, it separates off and it becomes its own field. And when it comes to the field of education, as in you go and get a degree in education, sorry, you're largely wasting your time, that is a philosophical degree. It is not an education in the math and sciences. And so they convince themselves that they don't need the stuff initially, and then when it dies out, others just don't even know that it's even a thing. And your only exposure from there on out would be over here. That's the unsatisfactory answer. Sorry. Can give you the full one in philosophy. Okay, any other questions? All right, so let's now get started with logic. So we're going to draw a quick pyramid over here. Do a big box for this. That feels like a bad piece of chalk. Always a good one. Good one doesn't fit. That's why it has bad one. Okay. So this is what we're going to call logic. And it is split up into propositional logic, propositional logic, predicate logic, and then logic with identity. We'll go over each of these. This is what we usually mean when we say logic. We mean these 3 things. So we're going to start here. Next week, we're going to do these 2. After that, after you have logic, we're now ready for set theory. Set theory we will only be touching in a very light way, unfortunately. And that will be what we cover our 3rd week of school. And then finally, we will get to geometry. The nice thing about this is I will introduce you to literally everything geometry presupposes. So we are building up the entire foundations for geometry. That's the point here. And then we'll start geometry our 4th week of school. Make sense? Okay, so propositional logic starting at the bottom of the pyramid. Starting out, we're talking about statements. We're going to get to logic. Logic is like very precise language. That's a high-level way you can think about it for now. So our very first definition now of the course, statement. What's a statement? A statement is a sentence that is either true or false, but not both. Make sense? Go ahead.
Good morning.
Good morning.
How are you?
Lovely. How are you?
Oh yeah? How are you? Good? Okay, I have your chips in my phone. How are your students all here today?
I think we're missing one, right?
Oh, do you? And what's this class called?
This is geometry.
Oh dear.
And I closed my list, so I don't know who I'm missing.
I think we're missing Samantha.
Oh, good thing the kids know.
Who is it?
Samantha.
Samantha? Oh dear.
She could just be in another room, though.
Okay,
She
yeah,
was- she's
it's
here
the
today.
first of the year, things
Yeah.
get kind of messed up. Sorry to interrupt you, but good morning, have a good day.
Thanks.
All right.
You skipped one.
So, sentence. Nope. Statement, I mean. What's a statement? A sentence that's either true or false, not both. We typically use Greek letters like alpha and beta to represent statements. Okay? All right. Example. Which of the following are statements? You're going to tell me yes or no. Is it a statement? Go back home. No. You guys are stubborn people. I tell you to do something, you say no. Go back home. No, it's not a statement. Next. 2 times 2 equals 5.
Yes.
No, it doesn't.
Yes, it's a statement.
Yes, it's a statement, though. 2 times 2 equals 5, that's a statement. It's something we can call true or false. 2 times 2 equals 4.
Yep.
Yes, statement. New York is a suburb of Los Angeles.
Yes, it's a
Yeah, it is. I've been there. Thursday up tar paper.
No, that's not.
No, that's nonsense. Can't call it true or false. The silliness of speedily.
That's awesome.
No. I am the most beautiful girl in town.
Yes, absolutely.
Yes! Finally. This statement is, second finally. This statement is false.
Yes.
Yes.
This is a trick one. You'll never get something this tricky on your homework. But no, this isn't a statement. Let's think about it.
Oh, is that
This statement is false. Is it true that this statement's false?
No.
So if it's true, it's false. Let's look at it the other way. This statement is false. No, it's not. So it's true. So if it's false, it's true. And if it's true, it's false. What's the conclusion? It's not a statement. What's a statement? A sentence that is either true or false, not both. We can't call it true. We can't call it false. So it's not a statement. And then the trickiest one. X plus 2 equals 5.
No.
Is that a statement?
No.
Yes.
No. Because it could be true or false.
Because it could be true or false. So it has a variable in here. And depending on the variable, it's either true or false. And so this is our first example of a predicate. So we'll come back and we'll have a lot more to say about predicates. So we're starting with propositional logic. We're going to move on to predicate logic next week, and we'll be dealing with things that look like this. So far, just talking about statements or propositions. Sorry. Statement, proposition, for the purposes of this class, they mean the exact same thing. Your book says statement, but everyone calls the field propositional logic. They don't call it statement logic. But it means pretty much the same thing. For those of you who want a bit of technicality to it, we would say, strictly speaking, a statement encodes a proposition. But for the purposes of this class, we'll use those words interchangeably. Statement, proposition, same thing. So we're starting out with statement logic or propositional logic. Okay. Jumped. Okay. Now, since we're talking about statements, we're talking about sentences, we're going to be interested in what are called sentential connectives. Sounds like a difficult name, but it's really a simple concept. What's a sentential connective? These are the terms or phrases that can be connected onto a sentence in some meaningful way. If I've got a sentence, and I can throw on some terms or phrases, and it still is meaningful, then that was a sentential connective. This is very broad. There's almost infinitely many sentential connectives. Examples. Not is a sentential connective, and, or, Jack believes, it is probably the case, if one statement, then another statement, if and only if. Those are all sentential connectives. What's an example of a not a sentential connective? Cal the yesterday. If I take some sentence and I attach onto it Cal the yesterday, I no longer have something meaningful. If I take some sentence and I attach onto it the up pigeons too, it is no longer meaningful. Let's give examples. So let alpha be, remember alpha now and beta are going to represent statements, sentences, same thing. So alpha is going to be the sky is green. So notice alpha is a statement. What is the value of alpha? Is it a true statement or a false statement?
False.
False. So alpha is false. Notice that with these statements, we can always call them true or false. Otherwise, they're not a statement. So alpha is going to be the sky is green. And we're going to let beta be 2 plus 2 is 4. Again, if we're saying beta is a statement, you better be able to call it true or false. What is beta? In this case, true. All right. We're going to look at some sentential connectives that we have listed up here. So let's look at and. Is and a sentential connective? The question is what I'm about to say meaningful? I tell you the sky is green and 2 plus 2 equals 4. Was that meaningful?
Yeah.
Yeah. Then and is a sentential connective. If it can be added on in a meaningful way, it's a sentential connective. Big word, simple concept. Or, if I tell you the sky is green, or 2 plus 2 is equal to 4, is it meaningful?
Yes.
Sentential connective. I tell you, if the sky is green, then 2 plus 2 equals 4. Sounds a bit nonsensical, but it's completely meaningful. I tell you, Jack believes the sky is green. Perfectly meaningful. I tell you, it is probably the case that 2 plus 2 equals 4. Perfectly meaningful. On the other hand, I tell you, Caldy yesterday, 2 plus 2 is 4. That's nonsense. So Caldy yesterday is not a sentential connective. Alright? So sentential connective, pretty simple so far. Terms of phrases we can add on to statements, maybe one, maybe multiple, in meaningful ways.
Can you do it with not?
Can you do it not?
Yeah.
Sure. The sky is not green. Okay. So in logic, we're going to be interested in statements, things that we can call either true or false, and we're going to be interested in very specific sentential connectives. Let us give you an example of a sentential connective we're going to be interested in. We're going to be interested in one that can take two statements and combine them together. So we can use sentential connectives to construct new statements, things that we call true or false, by combining existing statements together, things that we could call true or false. So we're going to look at New York is a suburb of Los Angeles. That's going to be one of our statements. Our other statement is I'm the most beautiful girl in town. And we're going to combine them with the sentential connective and. With me so far? And is going to be one of these words that we're interested in. And we call this, the and is a conjunction of these. So you have your first definition, statement. You have your second definition, sentential connectives. We got our third definition now, conjunction. If alpha and beta are statements, they're things that we can call either true or false. If alpha and beta are statements, then the new statement, alpha and beta, is called the conjunction of alpha and beta. Don't worry, there's only like 5 sentential connectives we're going to talk about. So, not very many. And's one of them. After this, we're already done with 20% of what we're talking about. Pretty simple. Okay, so if alpha and beta are statements, the statement alpha and beta is called the conjunction of alpha and beta. Good? Now, some notation really quick. We write alpha and beta as alpha and beta. That little upside down V means and. You'll get used to this notation as you get exposed to it. Now, those of you who have had a bit more classes with me, why should we be critical of this definition? If alpha and beta are statements, the statement alpha and beta is called the conjunction of alpha and beta. Why should we be critical of what I just said there?
There's more than just and.
Yeah.
The reason we should be critical is because I said alpha and beta is a statement. I know alpha is a statement, I know beta is a statement. How on earth am I justified in saying alpha and beta is a statement? How do I know I can call that whole thing either true or false? And so we've got to demonstrate that. The way we demonstrate that is with a truth table. So I'm going to start out and introduce you to your first truth table here. We're going to start with our statements. Our two statements are alpha and beta. That's what those letters are supposed to represent. Now, if I have two statements, what are all the possible values those statements could have? I could have alpha is a true statement and beta is a true statement. That's possible, right?
Right.
So I could have alpha is a true statement and beta is a true statement. I could have alpha is a true statement and beta is a false statement. I could have alpha is a false statement and beta is true. And finally, I could have alpha is false and beta is false. Those are all the possible combinations I can have if you give me two statements, alpha and beta. Go ahead.
So it's a 50-50 on whether it's a statement or not, because it could be completely true or completely false, and it can't be both.
If we are going to say that alpha and beta is a statement, it better always be a statement no matter what. Which means that no matter what alpha and beta are, we better be able to call alpha and beta true or false. So let's get comfortable with this. Grab 2 markers and a piece of chalk. Let's pretend that alpha is a statement, Donnie's holding a red marker. Beta is a statement, Donnie's holding a blue marker. I'm going to set up our first case here. We're setting up the case where alpha is true and beta is true. Question, is it true that Donnie's holding a red marker and Donnie's holding a blue marker?
Yes.
Yes.
Yes. So if alpha is a true statement and beta is a true statement, then alpha and beta
It's true.
is a true statement. Okay, let's set the next case. So I'm setting up case 2 here. I'm setting up alpha to be true, beta to be false. Right? Donnie's holding a red marker is true. Donnie's holding a blue marker is false. Question, is it true that Donnie's holding a red marker and Donnie's holding a blue marker?
No,
No.
it's false.
No. So if alpha is true and beta is false, alpha and beta is false. Next scenario. Setting up this scenario. Donnie's holding a red marker, false. Donnie's holding a blue marker, true. Is it true that I'm holding a red marker and I'm holding a blue marker?
No.
No. And then finally, if they're both false, it's true, right? I'm holding a red marker and I'm holding a blue marker.
No.
No, that's as false as it gets. Don't parrot me. Think. Stop. Think. Give me your answer, not my answer. I'm a liar. Don't trust me.
Got that rocket with us.
Okay. So, there's our truth table. Now, no matter what alpha and beta are, we know how to determine the truth or falsity of alpha and beta. So it is, in fact, a statement. So alpha and beta is a statement. We can always call it true or false. We knew alpha was a statement. We knew beta was a statement. Now, no matter what alpha and beta are, true or false, we always know how to call alpha and beta true or false. That's what our truth table tells us. These were all the possible combinations. Everyone understand how this now, we can call it a statement. It's always true or false. Statement, something that's always true or false. One of the two, not both. Okay, and then that's our notation. How do we determine the truth value of alpha and beta? We use truth tables. In general, you should always be able to construct a truth table for your statements. If you can't construct a truth table, then it's probably not a statement. You always have to be able to call it true or false. That's a better way to say it. So, if you can't figure out how to do that, it's probably not a statement. Alright, let's introduce another word. So, the word and. That's officially one of the words we're going to use in our logic. That word is never going away. And. One of our 5 special words. Let's try another word now. Let's think about another word like the word but. You with me? So, but is going to be a first example of a type of word we would never allow in our logic. Why would we not allow the word but in our logic? So, imagine some girl tells you, I love you, and I love your brother. Okay? I love you, and I love your brother. What's she saying? We know exactly what she's saying now. She's saying, I love you is true, and I love your brother is true. Right? Let's look at another sentence. I love you, but I love your brother. Is she saying that she loves you? Yeah. Is she saying that she loves your brother? Yeah. So this says the exact same thing as this. It's saying that this is true and this is true. Yet, do these two statements say the exact same thing?
No.
No, they say very different things. But does say that this is true and this is true. But there's something extra to it. It's somehow saying these two things are subtly connected. And you can never make perfectly explicit what that means. If I got 1,000 people in a room and asked them to give me a definition of and, they could all reproduce this truth table, and that's exactly what it means. If I got 1,000 people in a room and I have them all give me a definition of but, I'm going to get all sorts of varying definitions. It's vague. There's something imprecise about the word but. There's something ambiguous about it. It's somewhat open to interpretation. In logic, we only want words that are completely univocal. There's not open to interpretation. So, logic and math, we only want words like and. But that's a good word for a poem, where you want that ambiguity. You want to open it up to interpretation. Math, when I write a proof, I don't want any open to interpretation. It says exactly what it says. So when I talk to a computer, I use and a lot. When I talk to a computer, I never use the word but, because it's not nailed down. We don't know exactly what it means. So, in logic, we're only interested in the univocal parts of language. Univocal meaning one and only one interpretation. Unique one. Make sense? That's why we got and why we don't have but. Okay. So these these sentential connectives we've been talking about. So and is an example of one. Now we don't just want our sentential connectives to be sentential connectives. we want them to be truth functional sentential connectives. What does this mean? Here's a big definition, but it's simple to understand. So I'll give you the definition, we'll go through some examples, and then I'll go over the definition again, and I think you'll sink it. So what is a truth functional sentential connective? These are sentential connectives where the truth or falsity of the resulting statement can be completely determined from the truth or falsity of the component statements. Okay, that's a big mouthful. Let's get some examples, and we'll go over that again, and we'll make it make sense. So example, let alpha and beta be two statements. Alpha can be, the sky's green, beta can be 2 plus 2 equals 4. Doesn't matter, they're just statements. So far, what do I know about alpha? If it's a statement.
It's either true or false.
It's either true or false. That's what it is, because it's a statement. What do I know about beta?
It's either true or false.
It's either true or false, whatever it is. That's all we know about it. We don't know which particular statements they are, but whatever they are statements. So they're either true or false. Now we're going to try and draw a truth table for each of these. Truth functional sentential connectives essentially means you can construct a truth table for it. So let's construct a truth table. For Jack believes alpha. So first off, we have alpha. What are our possible values for alpha?
True.
True or false? I'm going to make up a symbol for Jack believes. And we'll do this JB mixed together. Jack believes. There's a symbol for Jack believes. Just making it up. Jack believes alpha. So let's see. Alpha's true. True or false? Jack believes alpha.
Good question. Who's Jack?
Can you determine it?
When I know Jack.
When you know Jack? Okay, I'm Jack. Ask me.
Do you believe it? Believe alpha?
Do I believe that 2 plus 2 equals 4? No, I don't.
Then it's false. Oh, it's
I lied to you though.
Yeah.
You can't just go around asking Jack. That doesn't answer anything. We don't do our math by taking surveys of people.
That's science, not math.
So if you know alpha is true, there is no way for you to determine whether Jack believes it.
Yeah.
So we can't say true, we can't say false. We can't finish this table. Jack believes is not a truth functional sentential connective. Let's read this one more time now that we've gone over that example. A sentential connective where the truth or falsity of the resulting statement can be completely determined from knowing the truth or falsity of the component statement. If I know alpha, does that mean I know Jack believes alpha? No. So this is not truth functional. Let's try another one. So moving on to the next one. It is not true that alpha. Okay, that's the one we're doing now. So our question is, it is not true that, we're wondering, is this a truth functional sentential connective? Okay? I'm going to come up with a symbol for it is not true that. It's going to be a crazy one. I'm going to do this horizontal line with a dink at the end. There we go. That means it is not true that alpha. Okay, let's test it. If alpha is true, then it is not true that alpha is
True. So it's false.
false. Let's give an example. We'll say alpha is 2 plus 2 equals 4. I say, it is not true that 2 plus 2 equals 4. Did I lie to you? Yes. You could say you're calling my sentence false. You're calling my statement false. If you could say you're lying, then it's a statement.
Yeah.
If you can say you're telling the truth, it's a statement. If you don't know how to say either of those, then it's not a statement. So, I tell you, it is not true that 2 plus 2 equals 4. You said, you're lying. It is true. So what I said was false. Alright? Now let's do an example where alpha is false. So alpha will be a statement 2 plus 2 equals 7. I say, it is not true that 2 plus 2 equals 7.
It's true.
Did I tell you the truth?
Yes.
Yes. So that one was a truth functional sentential connective. And sometimes we summarize that with just the word not. And we say not alpha. We'll have more to say about that one later. Alpha and beta. We already did that truth table. So I'll give a quick example. I tell you alpha is equal to true, beta is equal to false. Question. What is alpha and beta?
False.
Alpha is true, beta is false. Alpha and beta is
False.
false. We could call the whole thing false. So one more time we'll read this definition and then it should have sunk in, I think. Sentential connectives where the truth or falsity of the resulting statement can be completely determined from knowing the truth or falsity of the component statements. So the component statements, in this case, are alpha and beta, and the resulting statement is alpha and beta. We can completely determine the truth or falsity of alpha and beta by knowing the truth or falsity of alpha and beta. That makes sense? That's what we mean by truth functional sentential connective. In short, it means you can create a truth table for it. Let's do one more. It is probable that beta. Tell me, is this truth functional?
No.
If I know that beta is true, do I know that it's probable that beta is true?
No.
If something is the case, isn't it probable that it's the case?
No. No. Unlikely things happen.
Because unlikely things happen. Let's say betas, I won the lottery. Is it probable that I won the lottery?
No.
No, it just happened to be the case. So there's an example of one that's not a truth functional sentential connective. So we're only interested in the truth functional sentential connective, the ones that you can create truth tables for. Okay. If it's truth functional, we should be able to construct a truth table for it. Alright, said that. Alright, any questions about that so far? Before we move on to our second word of logic. So we got and, now we're moving on to our next word. Or. So if alpha and beta are statements, the statement alpha or beta is called the disjunction of alpha and beta. It is false if both alpha and beta are false, otherwise it's true. Notation. We write alpha or beta as alpha or beta. Again, you'll get comfortable with this notation. So and was the same thing as that, or is the same thing as flip it around. Let's do the truth table. Excuse me. All right, so we got alpha and beta are our two statements, and we got to OR them together, right? So I'm going to have alpha and beta. What are all the possible combinations for alpha and beta? I can have alpha is false and beta is true. I can have alpha is true and beta is false. I can have alpha is false and beta is false. I can have alpha is true and beta is true. I'm intentionally writing that in an annoying order so you don't get comfortable with the order. Order shouldn't matter then. But there's all our possible combinations for those four statements, right?
Yep.
Now let's look at alpha or beta. Well, once again, make alpha is Donnie's holding a red marker, beta is Donnie's holding a blue marker, and we'll set up each case. All right, so first case, make red false, blue true. Question, is this true? Donnie's holding a red marker or Donnie's holding a blue marker?
Yes.
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 One or the other is true, right? But it's also given to us in our definition. It's false if both alpha and beta are false, otherwise it's true. But in either case, true. Let's focus on the intuition anyways. All right, but let's swap it now. Is it true that I'm holding a red marker or I'm holding a blue marker?
Yes.
Yes. So second case, also true. I'm holding a red marker or I'm holding a blue marker?
False.
False. False.
False. I'm holding a red marker or I'm holding a blue marker?
Here. True.
True. Some of you might say that one feels a little bit weird, and that makes perfect sense, and we'll go over that weirdness. But in this case, it's true. Now, unfortunately, logic did not come from English. Logic existed long before English adopted logic. And so, we happen to choose the word or to capture this disjunction because it's the best word in the English language to capture it. But logic doesn't care about English. And so, in English, we use or two ways. We use it in what we call the inclusive sense, and we use it in what we call the exclusive sense. In logic, we mean it in the inclusive sense. So, I tell you, you must take physics or calculus to apply for my class. If you took both, is that okay?
Yeah.
Yes.
Yeah, so this is inclusive because it includes a case where you can have both. Let's look at exclusive or. You're at a restaurant, and the waiter tells you, that order comes with a side of salad or soup. And you say, wonderful, I'll take both. You say, no, that's not what we mean here. We mean it in the exclusive sense. You get one and not the other. So that is exclusive or. Now, exclusive or, using or this way, is perfectly valid, and we can add that symbol to our logic. So if you love that way of thinking about or, if we want to use it, then we write that as alpha x or beta, XOR meaning we mean or in its exclusive sense. And the symbol for that is or with a vertical line through it. We do or, and then we add another line like that for exclusive or. You can use it. It's a perfectly fine symbol. You can add this to your logic. In general, we don't care about it, and you don't have to remember it exists if you don't want to. So there's nothing wrong with it. We just don't like it. It's not it, it's us, right? We're breaking up with it. Okay, so that's disjunction or. So we did conjunction or and, we did disjunction or. Any questions about those so far? All right. Our next symbol, our next one is going to be not with its symbol back. So negation. If alpha is a statement, the statement alpha is false is called the negation of alpha. We also say not alpha. Notation. We write not alpha as horizontal line with a little dink at the end, alpha. So let's do a truth table for that. So here's alpha. Alpha, what are the possible values of alpha since it's a statement? True or false. Alpha is a statement. It has to be true or it has to be false. Okay, let's look at not alpha. If alpha is true, not alpha is
False.
false. It's the negation of it. Similarly, if alpha is false, not alpha is true. It's sometimes thought a lot like the negative symbol is thought of in arithmetic. Make sense so far? Negation. Now, negation on the surface looks like the simplest one of these, but it's actually not. It's very subtle and very tricky. I mean, I warned you about that ahead of time. So notice something here amazing. If alpha is true, not alpha has to be false. And if alpha is false, not alpha has to be true. In other words, alpha and not alpha always have to contradict each other. I can never say that the sky is blue and the sky is not blue. I can't have both of those being the case. One or the other has to be the case. If I'm writing an answer to a test, the answer is either 6 or it's not 6. There's no other options. It has to be 6 or not 6. Make sense? You think so. Let's get into it. Okay, so no, not alpha is the contradiction of alpha. We always know that either alpha is true and not alpha is false, or that alpha is false and not alpha is true. It has to be this case or this case. Okay, let's get a concrete example. So we're going to give you a bunch of examples of the contradiction or the negation of all swans are white. We're going to negate all swans are white. What's the negation of all swans are white? It's going to be that some swans are black, right? Those two are the contradiction of each other. Either all swans are white or some swans are black, right? Either all swans are white or some swans are black, right?
No.
No!
What if some are green?
What if some are green? So, if this is our alpha, we're trying to figure out which of these statements are equal to not alpha. So here's our alpha. If alpha is true, not alpha would have to be false. And if alpha is false, not alpha would have to be true, right? Let's imagine I live in a universe where all my swans are yellow. Question, are all swans white? No. Okay, so then some swans are black. No. So these are not negations of each other. If this is alpha, this statement is not alpha. Very subtle. When you have alpha and not alpha, they're contradictions of each other. One has to be true, one has to be false every single time no matter what. So if this is your alpha, this is not alpha. We are on a hunt now for not alpha. Okay, so let's see, could this one be its contradiction?
Yes.
Let's see, all swans are white, no swans are white. Those two contradict each other, right? Right?
Wait.
Right? I wouldn't say right that many times unless it was wrong, right? No, wrong. All right, let's go over it. Let's imagine that we live in a universe of all yellow swans. Are all swans white? No. Oh, so no swans are white?
Yes.
Yes. So it happened to work. Let's set a different universe. Our answer has to work in all possible universes. It has to be the case that anytime this is true, this has to be false. And anytime this is true, this has to be false. Let's try another universe. Let's have a universe where half our swans are white, half are black. Question, are all swans white?
No.
No. Oh, so no swans are white.
No.
No! So this is not the negation we're looking for. This is not the negation we're looking for. I wouldn't give you 3 in a row that aren't the negation we're looking for. So let's check the next one. All swans are white. Some swans are not white.
Yes. As
Is that a negation?
Yes. Yes.
Good, you're thinking, you're thinking. Let's set up some universes. We live in a universe of all yellow swans. Are all swans white? No. Oh, so some swans are not white.
Yes.
Yes.
Yes. Let's have another universe. Let's say we live in a universe of all white swans. Are there some swans that are not white?
No.
No. So then all swans are white.
Yes.
Yes.
Yes. So either all our swans are white or some of them aren't. These are contradictions of each other. This has to be the case, or this has to be the case. One of them has to be true, one of them has to be false. In any universe. Does that make sense? I told you, negation, it's the tricky one. So there's a good one. Alright. All swans are white. Not all swans are white.
Yeah. Yes.
Are those two negations of each other? Are they contradictions?
Yes.
Yes, that's the most straightforward one that there is. You want to negate a statement, put not in front of it. All swans are white? Let's not. Not all swans are white.
Simple.
Okay, simple. Simple negation there. Alright. Finally, all swans are white. Every swan is not white. Who thinks it is?
That's it.
Who thinks it's not? Can I take a side? Who thinks it is? Who thinks it's not? A lot of thinking here. Pick a universe. Let's go to halvesies. Half white, half black. Are all swans white?
No.
Oh, okay, then every swan is not white.
Okay.
No. Okay, so this one does not work. You getting it?
Yep.
Tricky, tricky.
Negation.
Alright, we'll go through some examples of these because the few I have are not enough. So here's an example of the types of things you'll be doing in your homework. State the negation of each of the following sentences. All men in Georgia are at least 6 feet tall. What's the negation?
There
No.
exists.
Not all men in Georgia.
Not all men in Georgia are at least 6 feet tall. That's the easiest way to say it. The more complex way to say it would be,
There exists a man in Georgia that is not 6 feet tall.
or using the same language we did before, some men in Georgia are not at least 6 feet tall. Another way we could have said it. Those are the negations of each other. Let's negate this. All students in France like geometry?
Some students in France.
Not no. Did you say no or not all?
I said not all.
Oh, sorry. Then that's correct. You can say, not all students in France like geometry. Or you could say,
Some students
in France don't like geometry.
some students in France don't like geometry. Either all students in France like geometry, or some students in France don't like geometry. Has to be one of those two cases. Every rectangle is a square.
Some rectangles are not squares.
Some rectangles are not squares. Every circle has a center.
Some circles are not squares.
Some circles do not have a center. Let's try a more complex one. For every pair of numbers a and b, a plus b is equal to b plus a.
There exists a pair of numbers a and b such that a plus b is not equal to b plus a.
That is correct. Now, not Caleb saying it.
For not every pair of numbers.
For not every pair of numbers is the same as finding one that is an exception.
Yeah.
So rather than saying for not every pair of numbers, we say there is some pair of numbers
But it's-
such that a plus b is not b plus a. Make sense? Trying to just give you a bunch of sentences to help your intuition develop here. Some men play golf.
No.
No, all no wait.
By you.
No, we're all. No, we're all what? Let's finish the thought.
No men play
No.
golf.
No or all.
No men play golf. I say, you tell me some men play golf. I say you liar? What am I saying if I'm calling you a liar?
No men
But-
I'm saying no men play golf. Just think, if someone said you're a liar, what would they be saying in each of these? That's what it is. So, I tell you there is at least one number x such that x plus 3 equals 7.
There is no.
And you say, you liar! What are you saying?
There's no
There is
number
not.
in x that
There's none.
x plus 3 will equal 7.
There is no number such that x plus 3 equals 7. I said that there is one, you call me a liar. So you're saying there isn't one. There is no number that makes that true. Alright?
Yep.
So get comfortable calling me a liar, and you'll get comfortable with the intuition for what the negation is here.
Makes sense.
Make sense? Alright. Let's negate a conjunction. Today is Monday, and the weather is cold. What's the negation of that?
Today is Monday and the weather's not cold.
Today is Monday, and the weather is not cold is a contradiction of that?
Today is not Monday and the weather's not cold.
Today is not Monday, and the weather is not cold.
Or today is not Monday.
Or
and
no,
the
no,
weather is
today
cold.
is not Monday or the weather is not cold.
Alright, let's try this way. So, let's try this and version first. So, how do I negate this not Caleb?
You put the not in and then you
Not Caleb. Alright,
He's calling you a liar. Just.
today is Monday, and the weather is cold. We're coming up with the negation for that.
Today is not Monday.
Today is not Monday, so you want to say today is not Monday. So, well, yeah, I'll write out. Today is not Monday. Okay.
and the weather's
No,
not
there's
cold.
no weather.
And we'll put our and symbol there so we see where one sentence ends. The weather is not cold. Okay. Let's think about this for a second. Fortunately, today's Monday, and fortunately, the weather's warm outside, right? Wouldn't call it cold. Well, we'll say it's hot outside. We'll pretend it's 100 degrees out there. Okay. Question: is it true that today is Monday and the weather is cold?
No.
No.
Oh, so then it must be the case that today is not Monday and the weather is not cold.
No, it's Monday.
No, it's Monday.
No, it's still Monday. So this is not the negation of this.
Right.
We're looking for the statement such that if this is true, this has to be false. If this is true, this has to be false.
The weather is hot and the weather is cold.
Sorry, what? So this statement should be what?
Today is Monday.
Today is Monday? So you're saying either today is Monday or today's Monday.
Today is Wednesday. Today's Monday or it's not. It's either Monday or it's not.
It's either Monday or it's not. Okay, we got that down. So either today's Monday or today's not Monday. When would this statement be false? Today is Monday and the weather is cold. How could we make this statement false?
When either one of them is
That's what I was saying.
When
the
what?
weather is warm or hot. Yeah, you could use an or.
How could we make this statement false? We could switch. It could be the case that today's not Monday. That's one way we can make it false. Or we can make so that the weather is not cold.
Yeah.
So if we switch that and for an or, there's a negation. So it's either the case that today's Monday and the weather is cold. That's true. Or it's going to be the case that today is not Monday or the weather is not cold.
Yep.
Pick any universe you want, and one of these has to be true, one of these has to be false. Because if this statement is false, if the statement today is Monday and the weather is cold is false, then either this portion had to be false or this portion had to be false. When is a conjunction false? When is alpha and beta false?
When one of them
Either
is
alpha
false.
or beta is false.
When this is false or this is false.
That's cool.
Make sense?
Yes.
Just a little scared. Let's make sure that we are completely clear. We can't overstress it. True, 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 false, false, true, false, false. Okay, if alpha is true and beta is true, alpha and beta is
True.
true. If alpha is true, beta is false, alpha and beta is
False.
false. If alpha is false and beta is true, alpha and beta is
False.
false. If alpha is false and beta is false, alpha and beta is
False.
false. So notice that alpha and beta is false anytime alpha is false or beta is false. If alpha is false, it's false. If beta is false, it's false. You see that? And so when is today is Monday and the weather is cold false? It's false when either today is not Monday or the weather is not cold. And so the negation of this is today is not Monday or the weather is not cold. Appealing to your intuition? Now, give you the algebra for that. What does that mean? That means when you have not alpha and beta, when you negate a conjunction, that is equal to not alpha or not beta. So when you distribute a not over an and, it switches it from and to or. Not alpha and beta is the same thing as not alpha or not beta. We'll prove that rule with the truth table, but that's the intuition for what we're seeing. Okay, so moving on now, you're coming up with the negation for each of these. All cats are black and all men are mortal. What's the negation?
Not all cats are black, or not all men are mortal.
Right, so it's going to be not all cats are black or not all men are mortal. That's how you negate it. You put a not on each of your statements and switch your and for an or. And then if we were to say that a bit differently, not all cats are black is the same thing as some cats are not black and some men are not mortal. Another way we could have said it. Perfectly valid.
Or some men are not mortal.
Right. Not all cats are black or not all men are mortal is the same thing as some cats are not black or some men are not mortal. Let's say the same thing. Okay? Let's negate the next one. Some rectangles are squares and some triangles are equilateral. What's the negation?
No rectangles are squares, or no triangles are equilateral.
Perfect. So take out the sum and put a no. Take out your and, put an or. Take out your sum and put a no. No rectangles are squares, or no triangles are equilateral. Okay? Let's try another one. Not the front row. Some widgets are gadgets, and no widgets are waggles.
No widgets are raggets.
No widgets are gadgets,
Or all wiggles or waggles.
or
Some.
wiggles or waggles. Not all, some. Good. Okay, so what have we been doing this whole time? We started out with alpha implies beta, and we were looking for its negation. So the negation of alpha, and did I say implies? Let me make sure. I do that a lot. I accidentally say the wrong word. When I do that, call me on it. If what I said didn't make sense, yell it to me, because I do that a ton. Okay, so we were looking for how to negate alpha and beta, right? We had alpha and beta, and we were looking for its negation, right?
Yes.
And what we're seeing is that not alpha and beta is the same thing as not alpha or not beta. That's the rule we're seeing in action here. Make sense? Okay. Now, we're going to negate a disjunction. So far we've been negating conjunctions. Now we're going to negate a disjunction. All right, not Caleb. Negate this. Think about what you're saying if you call me a liar. I tell you, I will study hard or I will fail. And I say, you liar. Or let's pretend you tell it to me. You tell me, I will study hard or I will fail. And I say, that's not true. What am I saying?
That you won't study hard and you will pass.
That I will not study hard.
And I will not pass.
Hard. And I will not pass. And I will
not fail.
not fail. If when you're doing these on your homework, you replace not fail with pass, stuff like that will be okay. So you could say on your homework, I will not study hard and I will pass. But so what did we do here? So we took the I will study hard and we negated it. I will not study hard, right? We replaced the or with an and then I will fail, we negated it. I will not fail. So when do we make an or false is another way to think about this. Let's do our truth table for or. So I'll put or there. Sorry, can you guys see that? This chalkboard's dead right here.
Yeah.
That's a, even when I scribble it more, it'll get much better. That's an or symbol. All right, so alpha or beta. If alpha's true and beta's true, true or true is?
True.
True. True or false is?
False. Or true.
True. Let's set that up.
It's true unless it's false.
I'm holding a red marker or I'm holding a blue marker.
That's true.
True. Trying to stay on camera. Alright. False or true is
True.
true. And then false or false is
False.
false. So when is an or false? When is a disjunction false?
When both alpha and beta are false.
When both alpha and beta are false. So I have an or here. I will study hard or I will fail. If I'm looking to negate it, I'm looking for when this is false. That's when this is false and this is false. So this is our alpha or beta. The negation of that is not alpha and not beta. You see it?
Yes.
Okay. So let's do some more. Just say it out loud. Next one. So we're negating this. Some will work or all will starve.
None will work and all will not starve.
None will work and all will not starve.
And.
And none will work and
You said one.
all.
Yeah, I thought he said and, but that's not your problem. So no, none will work and all will not starve. All will survive. Nope, nope.
Some will not.
None will work.
Some will not starve. You tell me some will work or all will starve. I say that's not true. They can turn into a little cannibal colony, right? Nobody works and last man standing is still there. They didn't all starve. One lived.
Some will starve.
Some will not starve.
So it's either the contradiction of this is none will work and some will not starve. Or in other words, some will live, right? None will work and some will still survive. I'll show you. Make sense? Okay, next one. Every triangle is isosceles or every triangle is right.
No triangles is isosceles and
No triangles.
Some triangles.
Some triangles are not right. Some triangles are not.
Say it again from the start.
Some triangles are isosceles and some triangles
Some triangles are isosceles.
are
Some
not
triangles.
isosceles and some triangles are
Some
not.
triangles are not isosceles and some triangles are not right.
Yeah.
Some in both, some not. Some triangles are not isosceles, and some triangles are not right. No roses are red, or some violets are blue.
Some roses are red and
Wait.
From the beginning,
some roses are red.
some roses are red,
and no violets.
and
No
No violets are blue.
no violets are blue. So negate this piece, and negate this piece. One piece at a time. So, not alpha or beta is logically equivalent to not alpha and not beta. That's how you distribute a not over an or. You negate each of the component statements and then switch out your or for an and. Okay. So that's not. We've had a lot to say about not, getting comfortable with not. Told you it's one of our harder ones to get comfortable with. Not versus never. Sometimes students want to think about not and never the same way. They are two different things. So the sky is not blue is very different from saying the sky is never blue. Both say that the sky is blue is false. Both are saying that the sky is not blue. Both are saying the sky is blue is false. But are still somehow saying different things. Never is somehow introducing time into the equation, right?
Yeah.
And time is a concept of physics. We're not at physics. This isn't a science. This isn't even a math. We're at logic. We don't have a concept of time, a definition of time in a logic course. So never and not, they say two different things. We are not in physics. We don't have a notion of time in logic. So not the same. Make sense? The difference between those two?
So we don't use never?
We never use never.
Never
We
use
always use not. Good?
Yeah.
It's just sometimes people often interpret not as never. So I wanted to catch you there. Because I've seen with past students that happen a lot. Okay, so now we're going to get to the concept of a proof before we introduce our fourth symbol up there. Now, you do this all the time. You try and convince someone of some fact. When we try to convince someone of the validity of some statement, we say, this is true because that is true. And somehow the that being true makes the this true. Right? I tried to convince you that Tom Brady is the greatest quarterback of all time. I say Tom Brady is the greatest quarterback of all time because of how many Super Bowls he's won. And his Super Bowl success is the reason I'm claiming that this is true. And if you think Super Bowl success, the greatest Super Bowl success makes you the greatest quarterback of all time, and you agree that Tom Brady has a great Super Bowl success, then you have to agree that he's the greatest quarterback of all time. So if you agree that the that is true, and you agree that the this necessarily follows from the that, then you will be convinced. So that's what it is to convince someone, to give them your reason for why you believe something. If they accept that the this follows from the that, which will mean that that implies this, we're getting to implies, and they agree that the that is true, then they'll agree that the this is true. So one of the ways that propositional logic can be summarized is it's the study of the rules for making correct propositions or correct statements. That's what propositional logic does. Makes correct propositions, correct statements. So proofs always consist, proofs is what we're going to be doing over and over again in this class. Constructing proofs, over and over again. Proofs always consist of statements of the form, if so-and-so is true, then such and such must also be true. How many of you know the Pythagorean theorem? Someone who's not Caleb, tell me.
A squared plus b squared equals c squared.
A squared plus b squared equals c squared is an equation, and it's not even a universally true equation.
Right.
So no, you're wrong. That is not a Pythagorean theorem. What does that have to do with anything? You just spat out an equation. What is the Pythagorean theorem?
Right.
Something now with right triangles. Okay, now we're starting to think about the theorem.
The hypotenuse squared is equal to the legs of the triangle.
Alright, he's getting at it. If we have a right triangle, notice how I started that with an if. If we have a right triangle where the legs have lengths A and B, and the hypotenuse has length C, then a squared plus b squared equals c squared. It's an if-then statement. If we have these conditions, then this conclusion is true. Every single theorem in mathematics can be rephrased into an if-then statement. Okay, so proofs are always of that form. If so-and-so is true, then such and such must also be true. Example. Basic algebra proofs that you do all the time. No one told you you were doing a proof, but it's what you were doing. If 3x equals 4, then x equals 4/3. It's a nice little proof. If 3x equals 4, divide both sides by 3, and you get x is equal to 4/3. Right?
Yeah.
Try another one. If a is equal to 2 and b is equal to 3, then a squared plus ab is equal to 10. Plug in 2 for a. So what's 2 squared?
4.
4. Plus a times b. What's 2 times 3?
6.
Why are you guys even here? You've mastered this stuff. And 4 plus 6 is? 10. Okay. So if this is true, then that is also true. Now, we never bothered to think about it as if then in our statement. In your algebra, you're told something like x is equal to 2. And you do some proof. Does x equal 2? No. You're saying if x equals 2, then this conclusion follows. It's not universally the case that x is equal to 2. It's just a variable. So you didn't think about it that way, but that's what you were doing. Okay. So all mathematical proofs are of the form if alpha, then beta. We call alpha the antecedent or the condition. I'll mostly use antecedents in this class. And we call beta the conclusion. Just terminology. Because we're going to be talking a lot about theorems, proofs. Okay. So now we're ready for our next symbol. Implies. Now, I told you not was the hardest one, but I think I said that, but I lied. Implies is the hardest one. But don't worry, the one after it's like the easiest one. And that'll be the last one. Okay, so implication now. So far we've talked about a conjunction, a disjunction, a negation. Now we're talking about an implication. Implies. Definition. Implication. If alpha and beta are statements, things that we can call true or false, then the new statement, alpha implies beta, is called an implication. We have tons of different ways of saying alpha implies beta. And so I'm going to say alpha implies beta a bunch of different ways. We also say if alpha, then beta. That says the same thing as alpha implies beta. We say beta if alpha. That says alpha implies beta. We say alpha only if beta. That says alpha implies beta. We say alpha is a sufficient condition for beta. That says alpha implies beta. And we say beta is a necessary condition for alpha. That says alpha implies beta. These are tons of different ways. In English, we say the exact same thing. And so one of the things we're going to try and get you comfortable with early on is using the exact same, or using a variety of language to say the exact same thing. What's up?
Is Jolie in your classes now? Are you in this one?
I meant to register for your class. It said 2 options for geometry. I clicked on the wrong one, and I went to your class because that's what I belong in. But registration said
Okay.
Mr. Donald's class. I'm trying to get in your class, but I didn't want to be late. So.
Okay, let's talk to Polly afterward and let's see what she does.
Thank you.
You can try and get someone to swap you if it's full.
There's
It's
somebody
not
here.
full. I'm really stupid. I really need the extra help.
You may need to go through it a bit slower, and that's okay. So do what's right for you. You can still learn all the material. We record all the stuff, and you always have access to my lectures anyways, because they're all recorded. But do what makes sense for you. Alright. So now, we've introduced all these different ways of saying the exact same thing. And it does not appeal to your intuition that those all say the exact same thing, most likely. So we're going to go through a bunch of sentences trying to develop that intuition. Okay, notation, we write alpha implies beta as alpha arrow beta. Alpha implies beta. So that's our symbol. So first thing we're going to do is put a bunch of these statements into the form if alpha then beta. So example, put the following in a if alpha then beta form. We're trying to figure out which one's the condition, which one's the conclusion. Which one's the antecedent, which one's the conclusion. So, if I eat strawberries, I get hives. What are we saying?
If I eat strawberries, then I get
Strawberries.
hives.
And then I get
Eating strawberries implies that you have hives.
So we're saying, if I eat strawberries, then I get hives. So that was an easy one.
Strawberries is the antecedent.
Eating strawberries is the antecedent, getting hives is the conclusion. Eating strawberries implies getting hives. If I ate strawberries, I for sure got hives. If I got hives, that does not mean I ate strawberries. Maybe I ate something else I'm allergic to. But eating strawberries implies getting hives. So in this case, you would just write, if I eat strawberries, then I get hives. Or then I will get hives if you want. I don't care if you clean up the English a little bit that way. Alright. People who don't study mathematics don't have good sense. What does that mean?
If people don't study mathematics, they won't have good sense. Then they won't have good sense.
If people don't study mathematics, they don't have good sense,
Then
They-
they won't have good sense.
then they won't have good sense.
Or they don't.
I don't care too much about the
If you
English
don't
there.
have- If you don't have
Which
good
one
sense, you
implies
don't
which?
study mathematics.
Does not studying mathematics imply not having good sense? Or does not having good sense imply not studying mathematics?
Not studying mathematics implies not having good sense.
If you don't study mathematics, you for sure don't have good sense. You can study mathematics and still not have good sense. That's possible.
But if you
But people who don't study mathematics for sure don't have good sense.
Yes.
So if you don't study mathematics, you for sure don't have good sense. That's the implication. If you don't study mathematics, then you don't have good sense. The crop will be saved if we have rain this week.
If
If
we have
we have rain this week, then the crops will be saved.
Perfect. Our condition this time is over here. We're saying if we have rain this week, then the crop will be saved. We're not saying if the crop will be saved, then we'll have rain this week. If you save the crop, it's going to make it rain. You're saying if it rains, then it'll save the crop. Good? All right, next one. It will rain tomorrow only if it gets cold.
If it gets cold, then it will rain tomorrow.
No.
That one works, because
If it will rain tomorrow, it means it's cold. If it's cold, it doesn't mean it's gonna rain.
Does it mean that raining tomorrow implying that it gets cold? Or is getting cold implying it rains tomorrow?
If it rains
tomorrow is
tomorrow,
implying it gets cold.
Raining tomorrow implies it gets cold?
Yes.
Which way does it go? It will rain tomorrow only if it gets cold.
getting cold is a
Getting
necessary
cold.
condition for it raining.
Implies
Yes.
Getting cold implies that it's going to rain? Or does it raining imply that it's going to get cold?
Raining implies that it is.
Does the rain imply the cold or the cold imply the rain?
The rain
The
implies.
rain implies the cold.
You sure?
Yes.
Yes, because it can get cold and not rain.
It can also rain and not get cold.
Not
This
because
isn't talking
only
about the
it.
physics of this world.
Yeah, but
It's
it's
saying-
only it.
Yeah.
Only if.
If and only if. It will rain tomorrow if and only if it's.
Okay, you guys are correct. Just want you to stick with it. Yes, it's saying it raining tomorrow implies it gets cold.
Yeah.
So notice something funny. If we got rid of the only there, then it flips it.
Yeah.
If I say it will rain tomorrow if it gets cold,
Then getting cold.
then getting cold means it will rain tomorrow. If I say it will rain tomorrow only if it will get cold, now it's saying it rain tomorrow implies it gets cold. Now, your intuition probably doesn't like that, so I'll give you one that your intuition is going to eat up. There is oxygen if there is fire. What does that mean?
There's fire.
There's fire, there's opposite.
Fire implies oxygen, right? Now I'm going to re-say the exact same thing. There is fire only if there is oxygen. Is it true that there's fire only if there's oxygen?
Yes. Fire.
Yes, and fire implies oxygen. If you have fire, you for sure have oxygen. If you have oxygen, do you have fire? We'd be in a lot of trouble, right?
Yeah.
So these both say the same thing. And notice how replacing if with only if makes out we have to swap our alpha and beta sides.
Right.
So there's oxygen if there's fire. That's true, since fire implies oxygen. There is fire only if there's oxygen. That's true, since fire implies oxygen. Make sense?
Yep.
So that's if and only if. The only swaps it on you.
Because it turns it from sufficient.
Okay. Let's do some more examples.
We just do that.
Huh?
It's a B and beta.
Oh.
No, we're swapping it now.
Oh.
Put the following in a beta if alpha form. So we want you to be your antecedent on the right, your conclusion on the left, with an if between them. That's what you're trying to do. If I eat strawberries, I get hives.
I get
I get
hives if I eat
hives.
strawberries.
Perfect. That's I get hives if I eat strawberries. Spell strawberries right. Okay. Next one. People who don't study mathematics don't have good sense.
If you don't study mathematics,
We're trying to get in this form.
You don't have good sense
You don't have
if you
good
don't
sense.
study mathematics.
Perfect. You don't have good sense if you don't study mathematics. All right, next one. If we have rain this week, then the crop will be saved.
the crop will be saved if we have rain this week.
Right, so she's just saying the conclusion first. The crop will be saved if, then the antecedent. We have rain this week. Good?
Yep.
Okay. It will rain tomorrow only if it gets cold.
If it gets cold, it will rain
Isn't-
tomorrow. Or no,
Isn't it just
that-
saying
that-
that it will
It
rain
rains
tomorrow?
tomorrow.
It will rain.
I'm not sure if I heard it yet.
If it will.
It doesn't start with an if. We do beta, if, alpha. Your if's in the middle.
He said
Oh.
it.
Oh, sorry. I heard you wrong. Say it again then.
It will rain tomorrow if it gets cold.
It will rain tomorrow if it gets cold.
Only
Oh,
if
it
it
will
gets
rain tomorrow.
We're stating it this way,
Yes.
Oh, yes.
so you don't get to use the word only.
Oh, okay.
You have to say beta, if, alpha. Which one's our beta?
It gets cold if it rains tomorrow.
It gets cold is our beta. It will rain tomorrow is our alpha. So we just say it gets cold if it rains tomorrow.
I literally said that.
Okay? You'll save yourself a lot of headache if you quickly look at the statement, identify your alpha and beta, and then look at the form you want it in. Alright? So let's do it that way this time. If there's fire, then there's oxygen. There's fire is our alpha. There's oxygen is our beta. Okay, now what's this?
Oxygen if there's fire.
There's oxygen if there's fire. All right. There's fire only if there's oxygen. Which one's alpha? Which one's our condition? Which one's our antecedent?
There's fire is our conclusion.
There's fire as our conclusion. Does fire imply oxygen or oxygen imply fire?
Fire.
Oxygen implies fire, so we're dying.
Fire implies oxygen.
Keep thinking about it.
Fire implies oxygen.
Your intuition is going to go back and forth on this.
Yeah.
It's going to click, and then it's going to be gone. And then it's going to click, and then it's going to be gone. And that's going to happen over and over again.
Yeah.
And that's just the way it goes. So, which one's our antecedent?
Fire.
The fire. So fire, here's our antecedent, here's our conclusion. And so what is it?
There's
There's
oxygen.
oxygen if there's fire.
Okay, make sense? Reading implications, not so easy. Okay, let's do super mini proofs. Alright, next one. What can you conclude given the following statement? So we're breaking this up into separate problems. This has nothing to do with this, has nothing to do with this, for example. So just focusing on this one. If Fred is on the team, he must go to bed early. Okay? Take that for granted. If Fred's on the team, he must go to bed early. I tell you, Fred goes to bed early. What can you conclude?
He's on
Then he's
the
on
team.
the
He must be on the team.
No.
No! Maybe he didn't make it on the team and he's depressed. Says, Mom, I want to talk. And he goes to bed early. Right?
Yeah.
On the other hand, I tell you, Fred does not go to bed early.
Then he's not on the team.
Then he's for sure not on the team. Because if he's on the team, he must go to bed early. Since he didn't go to bed early, he must not be on the team. Make sense?
Yes.
Let's play again. If a man is a postman, he has foot trouble. Okay? Now I grab Bob here, and Bob has perfect feet. What can you conclude about him?
He's
not.
He's not a postman. Because if he's a postman, he has foot trouble. Don't think about our universe and think, well, maybe he dealt with it. No. You only think about what I give you. If a man is a postman, he has foot trouble. This man has perfect feet. He's for sure not a postman. Now that man over there, he has foot trouble. So he must be the postman.
No.
No!
You're gonna get foot trouble from
He stepped on a nail. Poor guy. Right? Okay, next one. You'll be given a ticket only if you are a sophomore. Jean was given a ticket.
They are.
She's a sophomore.
She's a sophomore?
because you can only be given.
Only.
You'll be given a ticket only if you're a sophomore. Could there be extra tickets? Can't
That's
teach you
what
guys
they're
on this
only
one.
given.
Oh, did someone go back? Okay, you got it. You'll be given a ticket only if you're a sophomore. If Jean was given a ticket, she must be a sophomore. George is also a sophomore. Does he get a ticket?
Not necessarily.
Whoa. You'll be given a ticket only if you're a sophomore. He's a sophomore.
That doesn't mean they give.
That doesn't mean-
Sorry, we ran out of tickets. Right? We only have 5 tickets, and we only gave them to sophomores. So it is true that you'll be given a ticket only if you're a sophomore. Doesn't mean we have enough tickets for everyone. Sorry, George. Okay. Next one. The house will burn down if we don't get water. So I tell you that we do get some water.
House burn down. Doesn't matter.
No, we didn't
Might
do
not
fast
be
enough.
enough water.
It might not be enough water, right? The house is burning down. We throw a cup of water on it, save the day. No. On the other hand, we didn't get some
The
water.
house
The
burns
house
down.
burned
The house for sure burned down.
Yes.
Okay.
So pessimistic.
Did I do it?
Lincoln.
No.
Can't push it. Okay. So now that we've done a lot of implications, let's actually write out the truth table for this. And here's one that we're going to write out, and then I'm going to show it to you 2 weeks from now, and you're going to be confused by it all over again.
Yay.
It's one of those types of things. Alpha, beta, and we're looking at alpha implies beta. So alpha and beta are their statements. So what are all our possible combinations of statements here?
Alpha's true.
Alpha's
Beta's
true.
True, true,
False.
true, false.
False. True.
False, 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 false.
Perfect. Okay. We'll set these up with our markers. Alpha will be the red, beta will be the blue. First scenario. I tell you, if I'm holding a red marker, then I'm holding a blue marker. Is that true?
Right now it's true.
It's true.
Yeah.
Yes.
Not for now. Kind of ignore time. Every time you see me do this, This is the entire universe, me and these markers. There's no space, there's no time, there's just this existence right here, me and these markers. Don't bring physics into this. Okay, so in that case, it's true. Next one. If I'm holding a red marker, then I'm holding a blue marker.
True.
So chances are you don't want to call that true. Now the question is it false? If I'm holding a red marker, then I'm holding a blue marker. Am I lying to you? Is it false? No.
It's,
And if it's not false, what does not false equal?
True.
True. Not false is true.
It's vacuously
So
true?
it's what we call vacuously true. But that's good intuition for implication. Sometimes we don't want to call it true. So think instead, is it false? And your intuition is going to want to say, well, no, I can't call it false. And so if it's not false, then it's true.
Did you get that?
That's
Did you get that backwards? That's true. Implies
that's
false.
true and false.
Oh, did I set it up wrong?
Yes.
Sorry. Thank you for that. So we just barely did the third scenario. So we found out third scenario is true. Let me set up the second scenario. Second scenario, okay, is this. If I'm holding a red marker, then I'm holding a blue marker.
That's false.
That's false.
False. I lied to you. So in that case, we get false here. Okay.
That makes sense.
If I'm holding a red marker, then I'm holding a blue marker.
True.
Is it false?
No.
No, it's not false. What's not false?
True.
True.
True. So those two cases
Yeah.
where I wasn't holding a red marker, those ones we call vacuously true. If the antecedent is false, the conclusion or the implication is always true.
Right.
If the alpha part is false, the whole thing is always true. We call it vacuously true. I could start any implication with, if there's a purple elephant in the center of the sun, then, and whatever I say next, the whole thing's true.
Yeah.
If there's a purple elephant in the center of the sun, then 2 times 2 equals 19. That's true. It's vacuously true because the antecedent is false. There's no cases for us to check with the antecedent. Okay, so that is what we call vacuously true. Okay, the converse of an implication is switching the arrows. The converse of alpha implies beta is beta implies alpha.
Does it have the same?
Does it have the same truth table? That's the question we're going to answer now. I can put it over here. You guys okay with me writing it this way?
Yeah, sure.
So over here, we're going to write beta implies alpha. So set it up. Beta implies alpha. If I'm holding a blue marker, then I'm holding a red marker. True. All right, setting up this case. So I'll put the blue down. If I'm holding a blue marker, then I'm holding a red marker.
True.
True, vacuously true. If I'm holding a blue marker, then I'm holding a red marker.
False.
False. If I'm holding a blue marker, then I'm holding a red marker. Vacuously true. But true. So notice that beta implies alpha and alpha implies beta do not give the same things. Alpha implies beta is false in this case. Beta implies alpha is false in this case. They're false in different cases. This is one of the most common mistakes made in logic. Going from alpha implies beta to beta implies alpha. I can't say wearing shoes implies wearing socks and go conclude wearing socks implies wearing shoes. So the converse is very different from the implication. One of the most common mistakes in logic, accidentally going from alpha implies beta to beta implies alpha. They are different from each other. All right. We'll just state the converse of one of these and then keep going. So what's the converse here? If an animal is a man, then it is a human being. First off, is that true? If an animal is a man, then it's a human being.
Yes.
If you're a man, are you a human?
Yes.
Yes. Now let's look at the converse. If you're a human, are you a man?
No.
No, because you could be a woman. So the implication is true, the converse is not true. Let's try another one. Every man born in Indiana, is an American citizen. Is that true?
Yes.
Yes. And what's it saying? It's saying if you're born in Indiana, then you're an American citizen. Let's look at the converse. If you're an American citizen, are you born in Indiana?
No.
No. So the implication and the converse are very different things. If x minus y equals 3, then x is greater than y. Is that true?
For sure.
If x minus y equals 3, then x is greater than y. Is that true?
Yes.
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 Yes, because x is 3 bigger than y.
Yep.
When you have x and you take away all of y, you're still left with 3. Make sense?
That makes sense.
If I have 10 marbles and you have 7 marbles, then when you take away your marbles from my marbles, we're left with 3. Okay. Did we state the converse of that?
No.
Converse. If x is greater than y, then x minus y equals 3.
No. Not necessarily.
False. If plants are green, they must have sunshine.
Yes.
We'll assume that that's true. We'll assume chlorophyll needs sunshine. Let's look at the converse. If plants must have sunshine, then they're green.
No.
No, because they could be a different color and still need sunshine. You can still do photosynthesis and be yellow.
We don't discriminate.
If 2 plus 4 equals 5, then 4 plus 7 equals 10.
Vacuously true.
True. Vacuously true.
Oh, yeah.
Let's look at its converse. If 4 plus 7 equals 10, then 2 plus 4 equals 6.
Also vacuously true.
Also vacuously true. So in this case, the implication and its converse were both true.
I don't know.
All right. Now, we're going to introduce you to what is called the contrapositive. The contrapositive of alpha implies beta is not beta implies not alpha. This is called its contrapositive. Let's write out the truth table for the contrapositive. Close that for a sec. So, we're looking at not beta implies not alpha. Okay. I don't know why I drew that so big. Let's really quick write not alpha and not beta here. And then we'll write that. So here we'll write not alpha, here we'll write not beta, and then here we'll write not beta implies not alpha. Okay, so really quick, if alpha is true, what's not alpha?
False.
False.
False. If alpha is true, what's not alpha?
False.
If alpha is false, what's not alpha?
True.
And if alpha is false, what's not alpha?
True.
Okay, if beta is true, what's not beta?
False.
True.
True.
False.
False.
True.
Perfect. Okay, so now we're looking at not beta implies not alpha. So I'm looking at this implies this. So false implies false is
False.
It's
Or true. Sorry.
true. Vacuously true.
Yeah, it's true.
We're looking at not beta implies not alpha. True implies false is
false.
false.
Right.
Let's have that one. If I'm holding a red marker, then I'm holding a blue marker.
That's false.
False. True implies false is false.
False implies true.
So we're looking at not beta implies not alpha. So we're looking at false implies true. False implies true is
True.
true, vacuously true. If your antecedent is false, the implication is true. And then finally, true implies true is
True.
true. So notice with this one we got true, false, true, true. With this one we got true, false, true, true. Regardless of what your alpha and beta are, here's all their possible combinations. If alpha is true and beta is true, alpha implies beta, true. Not beta implies not alpha, true. If alpha is true and beta is false, alpha implies beta, false. Not beta implies not alpha, false. Etc. They give the exact same values regardless of the alpha and beta you plug in. That means that they're logically equivalent. You can think about them the exact same way. So, saying, if I'm wearing shoes, then I'm wearing socks, says the same thing as, if I'm not wearing socks, then I'm not wearing shoes. If I'm wearing shoes, I'm wearing socks. If I'm not wearing socks, I'm not wearing shoes. Make sense? So we'll do some examples now. Reopen up our projector. We did the truth table. Okay. So state the converse and then the contrapositive of each. So let's start with the converse. Converse, you just flip the implication around. So we got, if x equals 3, then x squared equals 9.
If x squared equals 9, then x equals 3.
So the converse would be 9 equals x squared implies x equals 3. Right? That would be the converse. Just flip the implication around. You guys okay with the arrow there?
Yeah.
The arrow is saying if this is true, then this is true.
Yes.
Okay, notice, if x equals 3, is it true that x squared equals 9?
Yes.
Yeah, what's 3 times 3? 9. Is it true that if 9 is equal to x squared, then x has to equal 3?
Yes.
Yes.
I don't know why I swap those. If x squared is equal to 9, if x squared equals 9, is it true that x equals 3?
Yeah.
Yes.
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 No.
I want to pause this long if it's not.
And negative 3.
X could be negative 3. What's negative 3 times negative 3?
9.
9. So if x equals 3, then x squared equals 9. That's true. But the converse is not the case. It is not true that if x squared equals 9, then x equals 3. Now let's look at the contrapositive. What's the contrapositive of this? The contrapositive of alpha implies beta is not beta implies not alpha. The contrapositive is if x squared is not equal to 9, then x is not equal to 3.
That is true.
If x squared is not 9, for sure x is not 3.
Yes.
Because if x was 3, x squared would be 9.
Yep.
Right? Let's do another one. If two lines intersect, they are not parallel.
They are not.
So first off, let's state the converse.
If they
Two lines are not parallel, then they intersect.
If two lines are not parallel, then they intersect. It just flips your antecedent and conclusion. Now let's take the contrapositive. If two lines intersect, they are not parallel. The contrapositive is
Two lines are parallel, they won't intersect.
if they are
they
parallel.
will not intersect.
If they are parallel, then they intersect. Or they do not intersect.
Do not intersect.
So with the contrapositive, you swap the order and then negate them both. Contrapositive, we kind of erased it, didn't we? So the contrapositive of alpha implies beta is not beta implies not alpha. So that's what we're doing. Swap the order, negate it. And this, swap and negate. Alright, let's forget about the converse now and let's just focus on the contrapositive. So, contrapositive of the next one. If food is sweet, then it has honey in it. What's the contrapositive of that?
If food does not have honey in it, then it is not sweet.
If food does not have honey in it, then it is not sweet. We're just swapping the order and negating them. Next one. If there is no atmosphere on Mars, then there is no life on Mars.
If there's life on Mars, then there's
If, go ahead. Okay, so this right here is saying, let's think about what this is implying. There's no atmosphere means that there's no life. Says the same thing as, if you have life, you have to have an atmosphere. No atmosphere means no life. Says the same thing as, if there's life, there has to be an atmosphere. Alpha implies beta is the same thing as not beta implies not alpha. See it? Next one. Oxygen is a necessary condition for fire.
Fire is not a necessary condition for oxygen.
Oxygen is a necessary condition for fire. What is that saying? Is that saying oxygen implies fire or fire implies oxygen?
Fire implies oxygen.
So that is saying fire
Oh, I see.
implies oxygen.
No oxygen is no fire.
Yeah.
Right.
So what's the contrapositive?
No oxygen implies.
Right, if it's not the case that you have oxygen,
Then there is no fire. There's no
then
oxygen.
it is the case that you do not have fire. Make sense?
Yep.
Okay. So, oh shoot, I erased our table of symbols we were keeping track of. So now we get to our last symbol. That was implies. So let's recap what we've talked about so far. What was the first one we talked about?
And
And
And what was its symbol?
the
down B.
An upside down B. Then we talked about
Or.
Or
what was this symbol?
A V.
The V. And then we talked about not. What was this symbol?
It's the weird stuff.
line with the
All right. And then now, and now we did what? Implies.
With the arrow.
Implies with the arrow. And now our last one is going to be equivalence, or if and only if. Logical equivalence, or if and only if. And that will be with a back and forth arrow like this. And will make sense why the back and forth arrow. Okay, so logical equivalence. All right, so observe that alpha if beta, oh, go ahead.
Did you intend to do 2 F's?
Yes,
So it's just like if.
we'll explain it right here.
Okay.
Okay, so what does alpha if beta mean? Which one's implying which one?
Alpha is implying. Or no, beta is
Beta is
implying alpha.
implying
Sorry.
This is saying you get alpha if you have beta.
Yes, so beta.
Beta.
I get hives if I eat strawberries means if I eat strawberries then I get hives. So this is saying beta implies alpha. Right? That's alpha if beta. So alpha if beta is the same thing as beta implies alpha. And alpha only if beta, what does that say?
Alpha implies beta.
Alpha only if beta says the same thing as alpha implies beta. There's fire only if there's oxygen, means fire implies oxygen. You with me? So alpha if beta means beta implies alpha. Alpha only if beta means alpha implies beta. Did I say that wrong? Let me say that one more time in case I said it wrong. Alpha implies beta means,
That one said it wrong.
let me try this again. Alpha if beta means beta implies alpha. Alpha only if beta means alpha implies beta. So notice how they're converses of each other.
Yep.
One says alpha implies beta, the other one says beta implies alpha. Okay, so then the common phrasing you will read is alpha if and only if beta. You are anding these two things together. When you say alpha if and only if beta, you're saying both alpha implies beta and beta implies alpha. So when I say alpha if and only if beta, we're saying alpha implies beta is true and beta implies alpha is true. They both imply each other.
That's good.
You with me?
Yep.
Okay. Since alpha if and only if beta is so frequently used, we write alpha if with 2 F's beta. And that means alpha if and only if beta. Make sense? Alright. Let's write out the truth table for this really quick. And then you'll see why this one's actually really easy. Okay. So we'll need some space. We're going to have an alpha. We're going to have a beta. We're going to have an alpha implies beta.
Beta implies alpha,
We're going to have a beta implies alpha.
and beta if and only
And then we're going to have alpha implies beta and beta implies alpha. So we're going to have alpha implies beta and beta implies alpha. Okay. So alpha and beta, these are statements. What are all the possible combinations we can have?
True, true.
true,
True, true, true, false,
false, true,
false, true,
false,
false, false. Okay. Now we're going to populate this row. Or sorry, this column. True implies true is
true,
true. True implies false is, this is the one that's false. If the antecedent is true and the conclusion is false, it's false.
Yes.
I tell you, if I wear a red shirt, I'll give you all A's. And I don't give you all A's.
You're
I lied. See? Lying. Okay. False implies true is vacuously true. And false implies false is
true,
vacuously true. Okay. Now we're looking at beta implies alpha. True implies true is
true,
true. False implies true is
true,
vacuously true. True implies false.
It's false.
false.
That's the false one. And then false implies false is
true,
true. Wonderful. Okay. So now over here, we're anding together these two things. So I'm anding this with this. That's all we're doing, right?
Yep.
So true and true is
true,
true. False and true is
false,
false and true is
false,
False.
False.
False and true is
False.
false. Okay. Yeah, repeating isn't an argument. Don't change your mind because someone repeats. True and false is
False.
false. And then finally, true and true is true. Okay. So notice, when was this whole thing true?
When both
When both were the same.
When alpha and beta were the same. If alpha and beta were both true, then it was true. If alpha and beta were both false, then it was true. Otherwise, it was false. So what do we mean when we say alpha implies beta and beta implies alpha? We mean that they have the same truth value. We mean they're both true or they're both false. And so we do this so much, we create a symbol for it. And this is what we mean with the back and forth arrow. Alpha, back and forth arrow, beta. It means they both imply each other or they're logically equivalent. They have the same value. So, first row, do alpha and beta have the same value?
Yes.
Yes. Second row, do alpha and beta have the same value?
No.
No. Third row, do alpha and beta have the same value? No. Fourth row, do alpha and beta have the same value? Yes. So that's all this is doing. And so we call that logical equivalence.
Makes sense.
They're logically equivalent. They have the same value. Make sense? And that is our last of our 5 symbols. So, now give you the actual definition of equivalence, which is what we just did. So, logical equivalence. We call the two statements alpha and beta logically equivalent, provided that alpha implies beta and beta implies alpha. We also call alpha implies beta and beta implies alpha a biconditional or an equivalence. I'll almost always say equivalence. I'll say they're logically equivalent. Notation, we write alpha if and only if beta as alpha, back and forth arrow, beta. We already did the truth table. Now, precedence of these operators. The precedence, the same way that you have precedence when you're doing like your arithmetic. If I did 2 times 3 plus 7 squared times 2, then you know the order that you carry out these things in. First you do the squaring, then you multiply the terms together, then you add it together. And there's a precedence that occurs. And you can usually guess the precedence from context. But here's the exact order. I think it will be very rare that you get confused. So first you apply your nots, then your ands, then your ors, then your implies, then your logical equivalences. Your logical equivalences, in logic, those are basically operate the same way as equals. And so equals is like the thing you evaluate last. All right, example. I have alpha implies beta is logically equivalent to not beta implies not alpha. So there's a bunch of symbols. What order do we evaluate these in? First, we would apply the knots. And then we would look at the implications. So if we put parentheses, it would be like that. So apply the knots first, then do your implications, then see if they're logically equivalent. Let's evaluate one of these just to see with particular values. Give me a value for alpha. True or false?
True.
True. Give me a value for beta.
False.
False. Let's evaluate one of these. So I'm going to plug in true and false and see what comes out. It's just like evaluating an algebraic expression. When you evaluate an algebraic expression, a number comes out. When we evaluate one of these expressions, we should get true or false coming out. So let's see. So we had true and false. Let's see. True implies false is? True implies false is?
False.
Okay. So we evaluate the implication. Is logically equivalent to, let's check. We'll put that there. Not false is true. And not true is
False.
false.
True implies false.
So far, I evaluated that, and I plugged in negative beta, negative alpha. Just evaluating, right? Okay. So we still have our false here. Let's see. True implies false is
False.
false. And then finally, is false logically equivalent to false?
Yes.
Yeah, so the whole thing evaluates to true. If you evaluate that expression plugging in these values, you get true. Make sense?
Makes sense. Yes.
Okay. So it turns out, if alpha were a true statement, if we said alpha is 2 plus 2 equals 4, and beta was the sky's green. And if I would have said this, 2 plus 2 being 4 implies the sky's green is logically equivalent to not 2 plus 2 not being 4 implying the sky is not equal to, the sky is not green.
Yeah.
Yeah, that sounds pretty logically equivalent.
Well, they are. It's just a contrapositive. Always says alpha implies beta is logically equivalent to its contrapositive.
Yeah.
So I gave you a tautology, so it will come out true no matter what you chose.
Yeah.
You could have made it false if you wanted to. But you probably didn't know it. Okay. Let's try another one. We have alpha or beta and not alpha. First, we evaluate the nots. So our first set of parentheses would go around not. Second, what do we do first? Ors or ands?
And I think
Ands. So then it would be like this. Ors and ands are the ones that are kind of hard for us to keep straight in our head. The rest are pretty intuitive. So we typically use parentheses every time we use ors and ands just to avoid confusion. The rest of them are pretty intuitive. All right, but so that's just a precedent. Okay. So, quick recap of everything we talked about. Statement. A statement or a proposition, same thing. A statement or proposition is a sentence that is either true or false, but not both. We introduced you to our 5 symbols, not, and, or, implied, and logical equivalents. And we went over some basic theorems. We said not alpha and beta is logically equivalent to not alpha or not beta. They'll say the same thing. Not alpha or beta is logically equivalent to not alpha and not beta. And we said alpha implies beta is logically equivalent to not beta implies not alpha. This one had the special name being the contrapositive. Remember, we left hanging x plus 2 equals 5, and we never came back and talked about that yet. That's a predicate. We'll be talking about that next week.
Yep.
That was not a statement. So that's propositional logic. Next week, we will be starting on predicate logic. Do you have any questions?
What about their existence for all symbols?
Those are called quantifiers. They will be introduced in predicate logic.
Okay.
Because you add quantifiers to convert a predicate to a proposition.
Sorry.
Any other questions? Wonderful. So we'll end the lecture there, and then we'll talk about homework.